So I'm Jeff Parker with Sediment County Soil and Water, part of the Upper Susquehanna Stream Team. We also have with us Mike Lovegreen, who's the Stream Team for the Upper Susquehanna Coalition's Coordinator. And we are putting together this virtual post-flood emergency stream intervention training program for all you folks who want to participate. So it's presented by the Upper Susquehanna Coalition. And we'll begin the program. The program is online at the Upper Susquehanna Coalition's website at www.u-s-c.org or the New York State website, which is there. And we can probably put that up at the end of the program so people have time to write that down. So I just wanted to let everyone know that's participating in this program that the Emergency Stream Intervention Program was actually developed in the mid-90s through a cooperative effort from the New York City Watershed Initiative in Delaware County Soil and Water Conservation District. Delaware County Soil and Water Conservation District and along with the USGS, because USGS was needed to do some of the stream stat stuff, that Delaware put together the first program in their county, and they actually offered a training session, a train the trainer kind of session, where we all went and visited while they were actually they ran the program for us, and they took us out to the field and showed us how to do some field measurements, and then we could actually go back during construction. So Delaware County, my hat's off to those folks. They did a tremendous job in getting this program developed. So the whole idea was to develop something and provide a practical tool or protocol or processes for municipal officials, us first responders, to actually address the stream channel corridor emergency situations. And this gave us the opportunity to incorporate the remedial practices that are needed so that in the future the stream itself could heal itself up naturally through that enhancement, and to understand the transportation function of streams so that we didn't go hog wild and make streams too wide, too deep, or whatever. This program was expanded to include all of New York State and developed for the northern tier of Pennsylvania along the New York State border. Training was also provided for federal and state regulatory agencies through this program after it was developed and taken over by the Upper Susquehanna Coalition through Tioga County Soil and Water Conservation District. So that's kind of where we are today. Precipitation. This is kind of where it all begins. Precipitation has a big impact on stream systems and their reactions. So we wanted to give you a little background data on the 24-hour, 100-year return period. The data was collected ending in the year 1993. You can see across the state we have anywhere from about 4.5 to 10 inches of rainfall, depending on where you're located in the state. Catskill region, of course, receives the most throughout the state. But in 1993, we were seeing 5 inches and 6 inches across the state. More research was done for the next 10-year period, and we can see there are some changes and some increases. The bar to the right now increases all the way till 13 inches. And if we back one slide, you can see we only used to have recorded around 10 inches prior years. So we're seeing increase in rainfalls for sure over this data set, and it's still occurring today. I haven't seen the new, if there's a new data set for the next 10-year period or not, but that would be interesting to take a look at sometime. This is all through the Northeast Regional Climate Center. So climate precipitation, weather patterns change, causing increased precipitation levels and variables. We're seeing more extremes than we used to. We're getting those localized storm events that are quick and fast and dump a lot of water in a short period of time. So those are very difficult to predict. And the severity of the forecast rain events are getting more difficult to predict. And once we get those types of rainfalls, where we get the deluge within a 45-minute period or an hour period, where we're getting up to almost 3.5 inches of rain in that short a time frame, the streams and all the stormwater systems have to adjust to those impacts and those increased flows. This slide is showing us average precipitation data set from the early 1900s to 2010, where it's showing the actual precipitation in the green lines with the spikes and the average precipitation and the trend we're seeing. If you look at from around 1970 onward to 2010, you can see we had a very lot of numbers of spikes in there for the average precipitation, reaching 50 inches a year or more. And a lot of those were probably recorded during certain storm events that we're seeing. You can see that our storm events seem to be increasing towards the end of this 2000 to 2010, where we've received a number of storm events which have increased our inches of flow. Of course, the tropical storms really brought this program to the forefront, the emergency stream intervention. And what we're dealing with is trying to figure out how to deal with emergency streams and the impacts that these storms have had on us. So Irene and Sandy really brought this program to the forefront, and it's being used across the state for highway departments, contractors, and also agency people. Stream mechanics, the next section. Of course, we begin with what is a watershed. The area of land with precipitation, rain, snow, etc., falls on and drains to one common waterway, such as a stream, lakes, estuaries, could be the local aquifer, could be a wetland area, and then eventually to the ocean. Why do streams look the way they do? Basically, geology for sure. Slope has a big impact on the way they look because of the steepness or the flatness of the area where the stream is migrating through. The types of soils, whether we have soils that can infiltrate some water into the soil that puts it into the groundwater, or if it's a heavy clay type soil with a fragipan, then we don't get much absorption into the groundwater in those areas. Takes a long time to get through to the groundwater with tighter clay soils. The amount of water that we have to deal with, like I said, those flashy storms, the timing of them, what time of year it is it in the time of year when we have vegetation growing? Is it at the time of year when we're starting to get into the late fall where we don't have as much vegetation growing? And that has an effect on it. The duration, of course, is the length of time that the storm impacts us. The magnitude would be the number of inches of rain or the rainfall amount and intensity that we have to deal with. And land use, of course, has a big impact, whether it's urban type setting, whether it's forested, whether it's agricultural. all that infrastructure that might be tied to that system within the river system itself, as far as highways and bridges and culverts and all that, have a big impact on why streams look the way they do. The river is the carpenter of its own deficit. So that's a very great quote that was given to us. Streams obey certain physical laws. They properly size themselves depending on how they need to transport the water and sediment. So streams transport both during a storm event. You notice that when we have a storm event, the water starts getting murky, starts carrying sediments, starts carrying even larger particles of material downstream as it tries to maintain its dimension, pattern, and profile based on the transportation of water and sediment. Streams move more than water. As the water moves over land, it picks up sediment and then begins to form the stream channel. Streams maintain their shape and size themselves as a result, again, by the volume of water, the amount of sediment they have to carry, and the type of sediment, whether it's a fine suspended light sediment or whether we get into a stream that has cobbles and larger boulders in it, and those can actually move and roll downhill, picking up more riverbed material and putting that in suspension. So depending on the sediments in the stream system and the types of geology of that stream system, really has a great impact on the shape and size the stream has to build itself to react to storm events. Stream channel, if it's A grading, that means it's depositing material, excess material, but if it's cutting down, it's removing that material. A stable sediment balance is that material moves through the reach without doing either of those two, so that it stays stable and doesn't try to erode or move around. So sediment balance, based on the ability of the stream to transport sediment, they adjust their shape, slope, and size. So depending on the amount of sediment the streams are trying to carry and the amount of water, basically changes the channel to do the work that it needs to do to move that material. Shear stress. Shear stress, the measurement of force that makes the sediment move. So it's kind of an erosive type measure. The deeper the water is, the greater the stress. The steeper the stream, of course, the more slope on it, the greater the stress. And so we need to look at those factors when we're dealing with sediment balance. And how does it stay in balance? Again, it's the natural erosion or the wearing away of rocks, sediments, soils by the action of water, wind, or even a glacier. That's degradation. And then the deposition, the accumulation or laying down of matter by a natural process, or the aggregation of the stream material. Generally, you'll see aggregation happening in the lower reaches of a larger watershed where the stream slopes aren't as steep. And then in the steeper sections of the watershed, you might see more erosion. Of course, we're going to see erosion in deposition areas too, as we'll see as we progress through the program. So we'll go through some examples of erosion: stream bank, mass failures, lateral migration, hoof shear, and we can actually see bedrock weathering by water. Stream bank erosion, probably one of the biggest impacts to a stream channel. When erosion such as this begins to happen on a steep bank such as this, very unstable, tons of sediment dropping into the stream channel during wet periods and high runoff, dumps that sediment into the stream, and the stream has to try to manage it or move it or transport it. So this is what creates some big changes in streams themselves, just because of the natural erosion process that might be happening, or the aggregated erosion process that was caused by some outside factor. Mass failures, they occur generally maybe because the stream undercut the toe of that steep bank and then the gravity pulled the material down. Or generally what we see a lot is that that steep embankment becomes saturated with the excess water that the rain event has given us, and it creates a slip plane underneath that, and then gravity pulls it down into the stream channel. But mass failures can have a big impact on the ability of a stream to transport sediment.
Jeff, just wanted to quickly mention on this slide here that quite often when we're looking at these sites, if you go to the top of the hill, a lot of times that slip slide or that saturation of soil is caused by a discharge of either a road ditch or drain tile or something like that. So when you're starting to remediate sites like this, it's always valuable to go to the top of the hill to see what might be causing some of these situations.
As we can see what happens to a stream channel, if you look downstream, you can see the width of the natural channel was a lot wider than it is now because of the failure and the amount of sediment that was brought into the channel. The upstream channel above the landslide was also about the same width as the downstream section, and now the stream itself is trying to adjust to that impact by trying to erode that material away so that it can get back to the state it was before the landslide. The lateral migration, this is an actual bank pin that was put into an eroding stream bank so that they could monitor the amount of erosion that occurred on an annual basis or biannual basis, whatever. You can see the white mark on the stake was where the bank was originally, and the dark re-rod from the white paint mark back to the existing bank is what has eroded over that time period. So streams do move laterally until they reach that point of equilibrium. So that's the stream bank erosion.
Jeff, yeah, I just wanted to chime in here that there are a lot of stream types that have raw banks like we're seeing in this picture here, and it's good to note that all streams move laterally over time. And again, we're talking about geologic time, but where you have a situation where you suspect that stream is experiencing accelerated erosion, we put in the bank pins like this so we can actually measure the rate of that erosion.
Yeah, that's a good idea, Mike, because that would actually give us an idea whether how soon we may need to do something depending on the impacts that are being created by the erosion or what it's impacting, if it's infrastructure or housing or something like that. So.
Right. So, sometimes we actually triangulate or put a bank pin or something like that we can measure from a stable situation. I know my experiences, we've put an awful lot of these pins into banks that might be 6 foot long and come back in the spring and the whole bank is gone, including the pin.
Of course, we deal with what we call hoof shear or cattle or animal non-exclusion of stream banks can have a big impact on how the vegetation can be established and make a stable stream. If you look downstream of the fence post there, you can see where the natural vegetation is stabilizing that bank quite well. And where we have animal access, we have some banks that are lack of vegetation that are starting to erode. And bedrock. Bedrock can weather. If you go to our gorges throughout the Finger Lakes, you can see natural bedrock weathering occurring. So those areas do erode too, not at the same rate as their gravel or soil valleys, but definitely get erosion from bedrock. Water has a very powerful effect. So we'll talk about some examples of deposition. Center bars, transverse bars, side bars, point bars, deposition at the mouth of the tributary, undersized hydraulic structures, deposition on floodplains, and a point bar. So this is a typical deposition of a center bar, which basically fills in the center of the channel. And you can see where the stream here is trying to get itself back or try to clean itself out so that it can be back on its original grade that it was on before the storm event. It's also trying to straighten itself out somewhat to where it was before, but the erosion that's occurring and the excess sediment that it's trying to move from that sediment bar or deposition center bar is probably larger than it can be moved during a normal rain event. So once that material gets packed in there by Mother Nature, sometimes it's difficult for the stream to adjust to it, and it starts to change direction and cause erosion on alternate bank areas. Transverse bar, kind of the same, but it goes across the channel on an angle, and it actually changes the flow of the stream. This one here, by the photo we're looking at, has created the stream to make it change and turn 90 degrees back into the bank on the right hand side of the slide. You can see where we have a tree starting to erode out from the impacts of this transverse bar. So these can cause stream bank erosion for sure.
Jeff, I just wanted to jump in here, if it's okay. The last two slides, the center bar and the transverse bar, you know, the reason that they become an area of concern is because if you look at those two slides, you see that center channel that's doing all the work of transporting both sediment and water has been braided or broken into a lot of little channels. And as a result of that, a lot of that energy has been dissipated. So there's no single channel that's carrying the work of transporting sediment. And as a result, you know, we have accelerated deposition in these areas, which then can complicate things. And as you can see in this slide, you know, it causes that channel to meander around and blow out banks and even add more sediment to the system. So again, that's one of the reasons why we're concerned about, you know, center bars and transverse bars.
Yeah, that's a good point. When the braided channel doesn't have the same velocities in it that it does if it's a single channel. So that's makes a lot of sense, Mike. I want to thank you for that.
Yep.
Sidebars. This sidebar here in this photo, you can see where the actual material is that has no vegetation growing on it. If you were to draw a line from the vegetation line on the right to the top of bank on the left, I bet they'd be about the same elevation. So that stream's probably flooding out into its floodplain when it's hitting that elevation. And that material that's on that sidebar generally is transported out of there during a storm event, and then when the peak storm slows down, it usually redeposits it there. So that's an active sidebar that probably should remain, and as you can see by the slide, really isn't causing any erosion problems on the opposite bank to the left. So sidebars are generally not a big problem unless they end up being bigger than this photo. Deposition at the mouth of a tributary. This happens quite a bit depending on the storm event and the watersheds. This tributary probably had a larger intense storm event that pushed all this material downstream towards the main channel, but maybe the watershed and the main channel wasn't impacted by the same storm. Therefore, it could not move that material out of there, or the watershed with the larger stream was up high enough that the smaller tributary couldn't get it out into the channel enough so it was transported. So this is an impact you'll see quite often on tributaries that come into a main channel. Undersized culverts. Generally, when we have undersized culverts, they cannot transport that material or that stream material through at the same rate as the channel it can upstream. So we end up getting depositions upstream of these culverts. Then the material drops out, and then maintenance has to occur. And you can see how this culvert here appears to be about half full of material now. The stream just slows down when it hits that undersized structure, and it just starts to lose its peak flow and drops material out upstream of the structure. Another example of the same issue, undersized culverts in this situation have allowed material to drop out upstream, creating a blockage of that channel. And then we have deposition on floodplains. So this is where we like to see the deposition, is actually on the floodplains. Generally, that's where the debris and finer materials will drop out of suspension. And if the stream is able to get into the floodplain during a storm event, it actually slows down, gets absorbed into that floodplain, and creates less erosion to the stream banks if we have good access to the floodplain. This is a point bar, kind of similar to the side bar, although it's a little bit larger. Point bars generally aren't a big issue unless we have over deposition that occurred during a storm event. This program will help us determine whether or not those are problems by doing a cross section and running it through the stream stats program. So this channel here is a pool riffle type channel, and it is the type of stream channel meander bends that you will always see these point bars develop. Generally, those point bars are active. As you can see, there's no vegetation growing on it. So the next storm event will come up, and it will actually strip some of that material off of that point bar and transport it downstream through the system. And when the peak storm drops down, then that material will redeposit almost in the same elevation as it was before the storm event. If we get an over deposition, it could cause excess erosion on the opposite bank if it's a storm event that really caused a problem, or we had debris pile up on that bar that created excess deposition. This is an example of how point bars form. Basically, when that point bar is starting to develop, it forces the channel to come around a meander bend. And instead of water flowing just kind of flat across the channel, it actually curls across the channel and creates a corkscrew effect, which has an erosion effect on that opposite bank. This erosion will occur until actually the stream itself reaches that meander bend equilibrium, and then it will slow down, but it's very difficult to determine when that will occur. Stream types. We're only going to discuss two main stream types in this program. The step pool sequence is usually found in the headwaters of the watershed on steep slopes. And then the riffle pool sequence streams are usually found in the broader valleys that have little flatter slopes and have more of a floodplain access to those stream channels. Step pool system is on those higher gradients, probably about 4% or greater. And you can see how they are very steep, very narrow, and they depend on a step and pool system in order to make themselves stable. The riffle pool is farther down in the landscape or farther down in the watershed where the slopes aren't as steep, and we're getting more meander bends in it, and we're getting more pools and riffles. The stream type step pool, this is a profile view of that. You can see how starting at the bottom of the slide, moving upstream, you can see how it actually builds itself in some steps. If you look at that photo where there's those three larger rocks in the foreground, and then behind it's the pool, that water's coming down the steep slope, dropping into that pool, and then coming out, reducing its energy and moving down the slope to the next pool. The stream itself will decide where the pools need to be and where the steps need to be. So these streams are very, very susceptible to damage if their maintenance is done on them improperly, because if you remove those steps within that system, we're going to increase the erosion. We're going to create a head cut and start losing the banks of the stream itself. Pool riffle system on the lower, in the lower parts of the watershed where there's more meandering occurring, actually act to slow down the velocities also. When the water comes over a riffle, it dives down into this pool system, slows down, and then comes back out of it at the tail of the pool, and then hits another riffle to, again, try to slow itself down. So those are the two stream types that we deal a lot with in New York. Floodplains. Floodplains, the area bordering the stream, constructed by the river and inundated during periods of high flow. This is a photo of a floodplain being activated right now by a larger stream system. When volume of water is such that the stream cannot contain the water in the channel, it has to use its floodplain. So basically, if you look at this cross section of a stream channel, we have base flow, which is the flow that's in the channel probably deep in the summertime, which is fed by groundwater. The bank full would be a storm event, which might be between 1.5 to 2 year storm event. And the 25-year flood looks like it's starting to access its floodplain. And then the 100-year, of course, is accessing that entire floodplain. Floodplains are very important to the stabilization of a stream, and they're necessary in order to keep the erosion down in the main channel. And of course, we all know floods are one of the most common natural hazards in New York and in a lot of the country. Floodplain function, we're trying to dissipate that energy during those flood events over a flatter floodplain area so that we can reduce the velocities, decrease the energy, and get the stream to maintain its natural channel. So floodplains help us do that. It lowers those peak flows due to the infiltration. Water is released more slowly downstream. It gives it a place to spread out, slow down, soak in. And rather than concentrating it all in one channel, all that water needs to spread out. It reduces the erosion in the channel. And it does give a place for the woody debris and deposition to naturally deposit. In fact, those floodplains on those larger valley floors are how the topsoil formation process works. Here's a slide showing after a major flood event in Franklin, New York. I believe it's Delaware County, showing the breadth of the width of this floodplain that was activated by this stream. You can see that it definitely put a lot of sediment in that floodplain and probably helped reduce the impacts downstream because it was actually engaged during that time.